Hello, I'm Paul Beckwith. In this video, I'm just going to chat about some recent research that was published about nitrous oxide emissions from permafrost. So I'm going to talk mostly about the highlights of the paper and a little bit about infrared spectroscopy. Need to explain how we measure these greenhouse gases, to very high sensitivity, so we can measure them in very low concentrations using lasers, tunable lasers, and a technique called spectroscopy. So I'm going to discuss all these things in this video, and in the next video I'll show you the details from the paper. So the paper is called Permafrost Nitrous Oxide Emissions Observed on a Landscape Scale Using the Airborne Eddy Covariance Method. So nitrous oxide, N2O, is a very powerful greenhouse gas. The global warming potential on the scale of 100 years is almost 300. It's something like 296. Now remember, for methane compared to CO2, which we talk about, CO2 of course is the most dominant. Methane is an ever increasing factor in absorption of energy, powerful in terms of the greenhouse gas effect. But nitrous oxide is 300 times CO2 roughly. Methane on a 100-year time scale is something like 34 times. On a 20-year time scale, methane goes up to 86. And on a year or two time scale, it goes up to about 150. But nitrous oxide, stable, fairly stable gas in the lower atmosphere. It's, like I say, 300 times almost. Now, nitrous oxide is produced mostly as a microbial byproduct. Okay, so microbes in soils, for example, as long as there's nitrogen available and oxygen available, then the nitrous oxide can be produced. So if the ground is saturated with water and there's not a lot of oxygen available, then that will suppress the production of nitrous oxide. So, like any microbial decomposition is just a chemical reaction. It's a biological reaction, but fundamentally it's a chemical reaction, and physics explains everything. So chemistry and biology, I would say that biology is a fundamental application of chemistry, and chemistry is a fundamental application of physics. So physics is at the core of everything, which is why I spent many years studying physics before I got into climate stuff. So temperature is important. So as temperature increases, chemical reaction rates increase. So in the Arctic, it's cold. It wasn't thought that the microbial decomposition would be significant. Also, when the ground's frozen, there's no microbial decomposition. So it's been thought that nitrous oxide emissions from the polar regions are minimal, whereas from the tropical regions, where it's much warmer, they're much, much higher. So, and also studies have been very limited. I mean, how do you go and measure these greenhouse gases? Well, one thing you can do is you can have like a small chamber or a cage covering about 1 square meter of surface area. You can have many of these chambers, maybe 50 of them, that would cover 50 square meters, and you can measure the gases that you trap within this container that are emitted from the soils or the permafrost. But the problem is that nitrous oxide emissions are highly variable depending on the type of terrain. What's there? Shrubs, marshes, open water, snow, ice, rock. It's very variable. So, if you're not really getting a decent sample. So there's a technique called the Airborne Eddy Covariance technique that actually in 2013 collected data. It was in August of 2013. You had a low-flying plane, about 15 meters above the surface. You had a detector to capture the gases that were rising from the surface. Then you had a spectrometer to accurately measure what gases were coming up at very high concentration, very high sensitivity levels, though, so you could detect very low concentrations of gases. And then the data was analyzed. And the problem is the data was collected for water vapor and for methane. It was also collected for nitrous oxide, but it was never analyzed, I guess, because this study has just come out, 6 years after the data collected. We're in 2019. The data was collected in August 2013. Now the paper comes out and is talking about the N2O measurements from those missions. So the problem is we haven't really measured N2O in the Arctic before. We thought it was minimal because it's cold and we didn't think it would be significant. And it's not significant in a lot of regions, but over certain surfaces, it's extremely significant. So this plane did many transverses across the north slope of Alaska, tested a region of 310 square kilometers in total. And like I say, the data has just been analyzed for nitrous oxide. The daily mean was measured to be 3.8 milligrams of nitrous oxide, N2O, per square meter per day, with a range of plus 0.9 or minus 1.6. So the range was, the data, 90%, with a 90% confidence, it's within the range of 2.2 to 4.7 milligrams of nitrous oxide per square meter per day. Well, what does that mean? If you take that average per day for the month of August, it would be 0.04 to 0.09 grams per square meter for the month of August. Now, the problem is this type of level of nitrous oxide, that's what we thought would be emitted in the entire year. Instead of that, it's emitted in a month. So emissions are actually 12 times higher than expected. What else is new? Everything's faster than expected with abrupt climate change. Everything is higher than expected or worse than expected. Now, I mentioned CO2, methane, we talk about CO2 as a greenhouse gas, methane, water vapor is a strong feedback. Nitrous oxide is the third most influential. Okay, it's inert in the lower atmosphere, but it rises up into the stratosphere. It's broken down by sunlight in a process called photolysis, or it's broken down by reacting with excited oxygen. So if you have oxygen atoms, they convert this N2O into nitrous oxides. NOx is where X gives 2, so that'd be NO2, NO3, etc. And these things, they catalyze the depletion of ozone. So we need the ozone layer in the stratosphere, of course, to keep the UV, the hard UV, from reaching the Earth, UVC. And we have a problem if the ozone layer depletes because life can't be supported at the surface. Okay, so this is ozone, or N2O is the dominant anthropogenic ozone depleting substance. Now, what are the sources of nitrous oxide? Industrial processes, agricultural practices that rely on heavy fertilization, plus there's natural sources. Okay, so like I said, the global warming potential over 100 years for nitrous oxide is 296 times that of CO2. The primary mechanism of N2O, regardless of whether it's anthropogenic or natural, is denitrification by soil microbes. So soil the microbes in the soil, they decompose the organic material, the nitrogen that is extracted, it combines with oxygen, produces the N2O. So human caused, it's the enhanced microbial action in the agricultural soils due to the imbalance between nitrogen fertilizer. We put loads of nitrogen fertilizer into the soils to fertilize the crops, but the crops don't intake all that nitrogen. So the excess nitrogen can react with oxygen, produce the nitrous oxide. So that's the biggest anthropogenic effects. And the natural effects are that tropical soils are considered the largest source. Emissions from permafrost have long been assumed to be negligible, and like I say, and they're ignored in current nitrous oxide budgets. The reason is that high latitudes are colder. Chemical reactions and biological reactions happen much slower in colder regions. Plus, we've got permafrost up there. We have very minimal microbial reaction, next to nothing in the frozen grounds, the permafrost. So nitrogen is limited up in the northern regions. So the biochemically inactive microbes are biochemically inactive basically relative to the tropics. So there's basically poor monitoring. We don't try to measure nitrous oxide in the tropics. So that's why this data that was collected in 2013 wasn't analyzed until now, is my speculation. So how do we measure? How do we really measure? If we want to do on-the-ground measurements of CO2 or methane or any other interactive gas, we can use towers, and we can measure the turbulent airflow in detectors moving up in the towers, and have these lasers and spectrometers to do spectroscopy to measure CO2 and methane. But we could do it for N2O, we just don't. But recently, in the Russian tundra, also in northern Finland, Lapland, there's several geological regions that have been found to emit high nitrous oxide, extremely high nitrous oxide. So this paper started thinking, well, where do we have N2O data? So they analyzed the data from the plains, and it's found that over bare peat surfaces, over thaw-induced permafrost collapse, so areas when when the permafrost thaws, there can be a slump, known as thermokarst. Those areas can produce lots of nitrous oxide. So the study focused on the data in 2013 was over the Alaska northern slope, the soils, etc. So, during the growing period, it was found that nitrous oxide was being produced in a sustained fashion. Finnish Lapland, it was found that thawing permafrost releases nitrous oxide. Permafrost contains 73 billion tons of nitrogen, which is 73 gigatons of nitrogen, just in the upper 3 meters of its soils. And how much is there? pH, water saturation, these things are all important. But we've only measured small regions in these sampling chambers. 1 square meter, maybe 50 chambers would be 50 square meters. And there's very high spatial variability, so a lot of regions don't produce any, so we missed it basically. But now we can, with the airborne eddy covariance method, now we've used this method for 30 years to measure CO2 and methane, etc., but we haven't looked for N2O. Okay, that's why the 6-year delay is there. So with new lasers and better spectrometers, we can use something called quantum cascade lasers. We can use fancy spectrometers, samplings, and we can get really high, good data. And the data was available, and just not analyzed for 6 years, basically. So basically, the sampling was done at 10 times a second. There's something called the BAT probe on the front of a plane. It's like a pitot tube on an aircraft. BAT stands for Best Airborne Turbulence, and it took the data. You could measure the velocity components, X, Y, Z of the winds, etc. Use these accurate spectrometers, which I'll explain in detail in the paper. You have a 25 centimeter path length cell. Light bounces back and forth 2,500 times, so effectively 625 meter path length, sensitive detectors, and classify the land it flies over, and we've detected huge amounts of nitrous oxide coming up. So in the next video, I'm going to show you the figures and images from the paper, explain a bit about infrared spectroscopy, and say why this information is extremely significant. So thank you for listening. And let me just bring you back the title of the paper again. My computer fell asleep while I was talking. Come on, computer, wake up. Okay, so this is a paper. It's open source, just released on April 3rd. Okay, permafrost nitrous oxide emissions observed on a landscape scale using the airborne eddy covariance method. So basically, there's lots of nitrous oxide in the Arctic. It's coming out as the permafrost thaws. We're getting more and more nitrous oxide coming out, and it's unaccounted for in all climate change models, etc., because we just didn't expect it to be coming out of the permafrost. Okay, so this is part 1. In part 2, like I said, I'll go into the details of this paper. I've given you most of the highlights. Anyway, thanks again for listening. Check out my blog, paulbeckwith.net.